This is a how-to video for log graphs. Now you're probably thinking that most look like this, capacitors or radioactivity, but they don't have to be. So we're going to look at some others and come back to this at the end. Here is a fairly common kind of question, something to do with practical and how you interpret it. So there'll be a scenario. Here we have water flowing out of a burette. The rate at which it flows slows down, takes longer. So you'll be given some data, okay, and this is a slightly adapted question where they have taken a set of results as it runs out over time. They've repeated it twice because it's going to change, it's going to be quite hard, and what they've done is they found the mean. They've also asked for the uncertainty. Okay, so what we've got in here is various changing values, and they're all fairly random. So the first obvious question is complete the gaps, fill in the table. So if you add all of those up and divide by 3, then what you'll get is 381.33. Practical questions, it's about the consistency of the data. So that will become 381. You're ignoring the 0.33s. Now, how do we get the uncertainty? Well, it's the classic way of doing it. Rather than looking at individual data, we're actually just looking at the repeat of the readings, and it goes from 379 to 385. So that's the difference of 6 between the minimum value and the maximum value. You want half the range. So that's going to be 3. If you do the same for the bottom one, you'll get 336, although it's actually 336.33. And the range will be 9 between the biggest and the smallest. So that should be 4.5, but again, consistency, you've got these. So you're going to round to the nearest value, which is going to be 5. Now, this will give you an exponential curve. So what they're getting you to do is produce a nice straight line from it. So you're going to need to see how the thing that changes exponentially, that's going to be the height. If you log that, then you should be able to get a straight line graph. But how do we do it? How do we get the uncertainty to go into our log graph? So the basic idea is, for the main value itself, all you're doing is you're going to log, natural log, that value 381.336. Okay, so the first one, we need to find the log of that. It goes to 5.943. And the second one, again, the main value 336, when you log that, you're going to come up with 5.817. And again, the numbers are not quite those, but you're rounding up to the same level as all the ones they've given you. Now, when you put in the uncertainty, it's not the log of this uncertainty. You've got to do it the old-fashioned way, which is where you take your biggest value and your smallest value, find the log of those, and then do just as you've done here. You find the range between them and halve them. Okay, so I'm going to use these values here. So it's going to go from 378 up to 384. Okay. It's not quite what you got here, but I'm actually using this data. So 378 up to 384 will give you a range of 0.015. And half of that is, of course, 0.0075. But again, that would be 4 digits. So I'm going to round it up to the next one. So that's 0.008. Replay that if you want to go through that and try and get that in your head. This one, similarly, if you find 331, that's 5 less, up to 341, what you'll end up with is a range in the values of 0.013. So the actual values are right at the edge here. It's 5.802, and it goes all the way up to 5.828. So you've got a range of 26 there, 28 minus 2 at the end. So you've got 16 between them. 26 between them. So half of that is going to be 13. So 0.013. Again, 3 decimal places in your digits. Okay, so you can't do the shortcuts like we do with normal numbers. As soon as you're starting to use powers, and as soon as you start to use logarithms, you're going to just have to work out the biggest value, the smallest value, and then half of the range. Okay, that always works if you want to do that for all of your data. Then they're going to say plot it on, and then have a go at plotting worst fit lines. Well, let's have a look at what we've got. So when you look at the graph, again, if you look at your data, your first one is actually the reading at time 0. So surprisingly enough, they're all exactly spot on, because you're not trying to time something as it moves, measure something as it moves. So there's no error bar on the first one, but after 10 seconds, which is this first line down here, so we're going up in tens, you've got a little bit of give or take. Now, on this scale, when you're reading 6349, plus or minus a bit, well, you've got 6.349. You can't actually plot, so it's actually 6.35 that they've plotted. Okay, now you will need to read and plot to the nearest half square, which is good because on here, this scale, this will be half a square. So that digit to the second decimal place is full squares, for the third one is part squares. So you're going to have a half square up and down. The second one is a bit bigger because, again, you can't go to 0.8 of a square, so you're going to go to the nearest half. So is it 0.005 or 0.010? It's going to be nearer to 10. So that's a full square on top. Okay, that's basically, we're saying plus or minus 0.01. Gets bigger. Again, that's 1 square. So that's just over 1.5 squares. So we're going to plot from their data point. They have 1.5 squares up, 1.5 squares down. So you're going to need to do the same thing on yours. As a technique, when you've got these large scales, get a line with a straight edge, ruler preferably, and you're going to go up and just mark the line for the 40. Okay, likewise, again, you can get it roughly in line so you know where it's going to go, and I'm going to put it down a bit. Put your line for your 50. So mark which is the right lines so that you're not plotting on the wrong one. Okay, that's helpful if you've got a really big graph. Then we're going to go for 5.943. So 5.9, 1, 2, 3, 4, and a half. So it's actually going to be nearer the halfway mark. So again, I'm going to go there, going to go across, and you are trying to get the right line. There we go. So there's your midpoint, and then you're going to go up. Basically, the nearest thing again is a whole square. So you're going to go a whole square up, a whole square down, and then just join them with your error bar. Okay, it doesn't need to be too neat, you know, try and be as neat as you can. But as long as you can see that it's the nearest half square, they're going to give you that mark. Now they will put an overlay on, so you'll see straight away if you've got the right one. So therefore, anything that makes it easier, you know, if you want to put a mark going across, like I've done, a dot there, that'll work. Likewise here, going up for the 50 seconds, 5.817, so 5.8, 1, and it's going to be a half. So again, going to go across, and it's going to be there. So there's my cross, and I'm going up 1.5 squares. So half, 1 square, make sure your middle's clear, down half and 1 square. So that's quite a large error bar. Okay, so you've plotted your point and you've plotted the error bars. There's a lot of marks in there. Doesn't take too long, but just be careful. It's worth a lot of marks. They're easy marks, so don't fluff it up. Now, if we then do the line of best fits, well, it needs to go through all of your error bars. Now we know that the top one up here is fixed, but that doesn't mean anything. You still need to fit all of your data. Now if I put my line underneath, that's very wonky down. If I put it above, you can see they're not in line. You do have scatter on your graph. So you're still going to have to try to fit the data as best you can. And I'm doing it upside down, so a bit cack-handed here. And see how it slips. It's too easy to slip. So again, do this in pencil. I'm doing this in pen because it shows up better on the video. That just happens to go to the value at the top, but that's by sheer coincidence. You've got to scatter all the way along, a bit above, a bit below, a bit below. Yeah, pretty good. Okay. Do it in pencil. If you're not sure, rub it out, do it again. So these are random errors. You can see them all the way. That's the point of the error bars. They're all going to have a little bit of uncertainty, randomness built in. However, that and that is not within the error bars. Those two are starting to look a bit anomalous. It's more likely to just be 2 rather than the other 6, but you never know. Okay, so line of best fit, the best you can. Next question underneath the graph says determine your gradient of your line. Well, if you have a gradient that goes down, draw it all the way to the axis. Okay, so this is going to be 6.5 minus, again, I do it on the graph, make it easier for yourself. It's not 0. 6.5 minus 5.6. Okay, so that's equals 0.9. So that's the log of h. It's not h on its own. Okay, just a quick reminder, because it was a snap, h is the height of water that you've got in your burette. Down at the bottom, now I know it starts at 0, but again, just get into the habit. So that's, again, to the nearest square, it actually just happens to be 65. So there we go. So I'm going to go 65 minus 0. Because I'm double checking, I'm just getting into the habit of doing it. So 65. So gradient of your line, which I haven't worked out in advance. So gradient dy by dx, if you want to put that in, it just makes it really obvious. You've got 0.9 divided by 65, whatever that value is. Luckily we have the calculator here, so 0.9 divide 65. 0.0138. Okay, now 0.014 is more realistic because 2 sig fig, 1 sig fig. Well, you have got 2 there because you're actually doing it far more carefully. You're not to the nearest grid line, you're actually going better. So you do have 2 sig figs. You got 2 sig fig there. Again, you could actually say that's 3. Okay, 0.0, excuse me. So yeah, you've always got 1 more than you're actually reading off. You could say that's 3, so you can get away with that. Okay, 3 sig fig is always what you get on a graph. Big squares, little squares, and then parts of squares. So if you then fit that to an equation as is standard, then you're going to have a little bit of easy to see where things are going. So this one here, we don't know what h is, we don't know what lambda is, we're trying to work those out. They are of course noted somewhere in the question, but it doesn't usually matter too much. In this case I don't think they have a meaning. So let's get rid of it. Log of h equals natural log of h, natural log of capital H, and that's going to be log of e, which is going to get rid of that, minus lambda t. So you have t on your x-axis. That's therefore got to be the gradient, because that's your multiplying factor. Is it a negative gradient? Yes, your graph goes down, so that agrees. Log of h is on the y-axis. That's okay. So that must be your intercept. So nice and straightforward for this. Value for a lambda, you're just taking that value there, 138, and your value for h is literally 6.5. Or is it? Let's have a quick check. It's a log graph. You have log h, so what you're going to do is find the second function of log, natural log, for 6.5. So you are going to do your second function e and put your 6.5 in. Okay, so the value is actually 665.14, which is, in our context, the original starting depth. Except it wasn't, was it? It was 665, not 0.14. But that is showing us the measurement uncertainty. So that has a valid reason. It doesn't have to be exactly 665. So 665.14. Okay. And then with all questions, they're going to do something about it. The rest of it is about the actual practical skills in terms of their interpretation of meaning, but that is fairly standard. If the error bars are big, they may well ask you to draw a line of worst fit. Now, if they were, again, you're taking your line and you're just making sure it goes through all of your error bars. Okay, and that's the only thing to check. Now, I can't do it on here because there is too much scatter. But if all of them line up, the worst one through your error bars, and if you find the value of that one, that is your give or take, that is your uncertainty on the value of the gradient. And even if you've calculated something, rather than just here, our value thereafter is equal to, so if you have to calculate something from your gradient, it'll still be give or take that same percentage or that same fraction. Okay, so that's really quite common. As I say, there's a little bit here which says suggest a possible source of systematic error in your burette. So there is systematic error because that's what causes that to be off at the top. That's your systematic. And that's the thing that you can see. It'll be off by the same amount all the way down. Suggest a source of random error. That's what's causing these. So that range there, that's going to cause by your randoms. Okay, so a few key little hints there with that. But what you're after is the actual possible things that could be off in this experiment. And that's really about looking back at this and finding out what may have caused that. And the systematic error is probably going to be not so much this. The clue is if anything to do with time, it will be the timer. That's your systematic error. Okay, it's going to be the give or take uncertainty within your timing. Random errors, again, you've got those different bits and pieces that make it all work, so you can come up with those bits, leakages or whatever in this case. So that's a quick run through of one practical. Here's another one that we'll do much more quickly, but again, this is a different way of looking at exponentials. So this one's a bit more visual, completely different context, and it's suggesting that amplitudes decay exponentially. So a student has a rocking ruler, they balance it on top of something, and as it bounces up and down, as it says here, they're going to video it, use a video recorder, and then work back in slow motion to take readings. And they have taken some readings. Voila. Top displacement, bottom displacement, hence it's going up and down. And they're finding that maximum displacement, that maximum amplitude as it changes. And they've done the graph for you. Okay, so here's an interesting one. Here's our top data. Here's our bottom data. On the line, on the graph it says draw the lines. I'll start with the third one, which is just to get the single parallel one from the equilibrium position. You don't know what that is, but you can take an educated guess when you do this. The chances are it's going to be half of your starting place if they've set it up nice and horizontally. So that's a shade under 25, so that's going to be 12.5. It doesn't work. Why? Because who says it goes all the way down to 0? So they might start it at 25, but coming out later, you know, it's not going to go all the way down. So how do we do that? You do it in the order the questions given. Okay, so draw a line showing how the top one varies with n and how the bottom one. As it's upside down, I'll do the bottom one first. So again, a little clue for you. When you're drawing curves, if you have to draw curves, just run it over a few times. If you've got a pencil, which I haven't, if you've got that, then you let it run through, do a faint mark, and then you join the best you can over your faint mark and get rid of the faint mark. Likewise here, if you have to do it, or if you're good at this and feeling artistic, then again, a bit like golf, you are practicing your swing, you're practicing your curve before you do this, and you're going to run it through. Again, that's not too bad. Do not attempt it in pen. I've had years of training. So, the last one, parallel to the horizontal axis to mark the equilibrium position, it's going to be symmetrical. Okay, these two lines should be symmetrical if they are decaying away to that center point. So what you want to do is just find that value, a convenient value where they are. So if we go down here, 1, 2, 3, 4, 5, 6, 7, 8, you get the idea, 9, 10, 11, 12, and count all the way down. And if you, it looks like it's 12, 2, 4, 6, 8, 10, 12, 13, so it's actually halfway down, so it's another half square. And then you can put your line across. Okay, so there's one mark on each of those, but it should be symmetrical. Okay, there you go, nice and simple. So that's an easy-ish set of 2 marks. Surprisingly hard though, so it's almost worth practicing a few curves. And then it says, for this question, where's the exponential come in? Okay, so how do you check it's exponential? Well, it's a fairly simple process. You want a nice big reading, so you know, if you want to go really thorough, then you're going to go through all of them and measure the top to the bottom. The other way of doing it is simply go, well, I've got a height. What is my height from, say, there? After 5 seconds or 3 seconds, it doesn't really matter which. I'm going to go for 3 seconds. There we go. What's our height? So height 1, height 2, 3 seconds later, height 3. There we go. And you could actually use your data off your data table if you want. Height 4, because they should all work. It was done with freeze frame on a camera, so they should all be good. And what you're after is basically that change should go down by the same amount. So if you find your height from your center line, excuse me, I'll show you, height, and subtract that height, okay, you'll have your delta there. That delta, okay, excuse me, will be smaller. That one will be smaller again. It's always good to do it 3 times, but at least twice. And that should be proportional to how much you've got. That should be proportional to how much you've got. Likewise, that one. Okay, so you're comparing that size there, n, compared to the change in n. Again, n2, change in n2. Okay, so delta n2. Delta n3 compared to 3. So just do it as a fraction. So occasionally those come up. You just be systematic. It's going to be like you do with radioactivity. The rest of them tend to be that nice log graph, and therefore working things out from your gradient. Okay, so that's short thing. Practice it. Have a look back now at your capacitors test, okay, and go through those. I'll record this separately, so if you're really stuck, I'll talk through on this one.